3 days a week office. So cool. And that's what my classes were like in when I was a student at community college, because I worked Friday, Saturday, Sunday in the restaurant, right? All right, so Diego sent me a problem from 4-6. This is homework 19. I don't know what number it is. It doesn't matter. But they gave me a rational function of x minus 2 over x times x minus 3. You will have one that you will have to factor. This one is already factored, right? And it says solve the inequality using the graph. Let's do it with the table and then verify with the graph, okay? Because you're going to have to do it with the sign table when you do it on the test. So, but I can clearly see points and pieces of like a 1 over x kind of deal, right? And so look at the inequality that they want. They want r of x less than 0, right? So for me, how I say that, I say it as I want places where the graph is underground and not touching the ground. So I want the places where the graph is underground and not touching the ground. So I'm going to highlight all of that in blue, right? And so you can see that's the piece I want. That's the interval I want. And I can already see the answer, right? It's so r of x is less than 0 when x belongs to negative infinity to 0, union 2 to 4. And so you can clearly see, right, that highlighted blue piece is between x is 2 and x is 4. And it can't be equal to 2 because it says less than 0. If it said less than or equal to 0, Diego, you with me there?
Yeah.
Right? So you got to be thinking less than is underground, greater than is above ground, right? But let's do it with the sign table. What are my critical values? Well, I need when the numerator is 0 or the denominator is 0. So I have 0 and 2 and 3, right? When the downstairs is equal to 0 at 0 and 3, and the upstairs is equal to 0 at 2. Oh, that's a 3. I'm sorry, it's not a 4, it's a 3. I had my graph wrong. Sorry, it's a 3 there, sorry. And so I set up my sign table. I know I go from minus infinity to 0 to 2 to 3 to infinity. And everything's got an open paren on it because I cannot use it, right? Everything has an open paren on it because I cannot use it. And then I want my factors to come up with my rows. So I have a factor of x minus 2, a factor of x, and a factor of x minus 3, and then the whole thing will give me my r of x. I want to see this, whether MathXL asks you for this or not, I want to see it, right? And so what are my test values? Well, I can pick anything I want. Let's pick -1, let's pick 1, let's pick 2.5, let's pick 4. Anything I want, left of, right of, and in between, right? My criticals. And now I'm checking my signs, right? So when I plug in a -1 into all of these factors, I get negative, 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 so the whole product is negative. And that's good. I want that, right? So I know I want the interval from negative infinity to 0. When I plug in 1, I get negative, positive, negative, so that's a positive. I don't want it above ground. I want it below ground. When I plug in 2.5, I get positive, positive, negative, so that's good. That's negative. I want that interval from 2 to 3, and when I plug in 4, I get all positives. I don't want that interval. And so you can see I want the union. There's my answer, the union of those two pieces. Sometimes MathXL will ask you for the two pieces separated, but I like them written as a union. What do you think, Diego? Any
Yeah, yeah, I got it. I got it.
It's easy from the graph, am I right?
Yeah,
Oh,
like when you use the graph, it's way more easier than how I did it.
exactly. So you're going to cheat. You're going to use the graph and then use the sign table to verify what you obviously know from the graph. Right? On the test, you're going to graph it on your calculator. You're going to be able to answer the question right away. And then you create the sign table to show me that you could have done this problem in the year, 1890.
Okay, thank you.
Yes. And I apologize. It was really bad of me. I just was, I had a big end of the season party with my golf league on Friday and just kind of lasted all weekend. Alejandro says, is what's the Alejandro? What are you saying there? HY or Y is? Oh, okay. Oh, yes, I got it. Y is right. So when remember my function is the quotient or product of all of those factors. So when I'm multiplying an odd number of negatives together, I get a negative. When I'm multiplying an even or dividing an even number of negatives together, I get a positive. You with me there? Oh, right. Good, good. Thank you. All right, this is from Sean. Nice. This is perfect. This one's perfect, okay? So I'm going to give you the function. This is from homework 14 or 3.3. I'm going to give you the function 4x squared minus 24x plus 33 and ask you to show me the transformation of the mother function. What is the mother function here?
Quadratic.
Say it again, Alan?
Quadratic.
Yes, and even simpler, 4x squared, right? Just that leading piece, right? Eventually this thing is going to look just like 4x squared. Eventually we're going to become our parents. So I'm going to start with factoring out the 4 from the first two terms. And every step I do, now if I distribute that 4 back, I should get back to my original function, and I do, right? This is the mother. I want to find k. K is negative 6. I want to find half of k. That's negative 3. And I want to take half of k and square the heck out of it, and I get 9. I'm going to add 9 on the inside and subtract that result from the outside. And notice I get a 4 times 9 here, right? Notice I get a 4 times 9. That's a 36. I have to cancel that 36. Sean, you with me?
Yeah, I'm with you so far.
Good. What does this piece always factor into every single time? X plus half of k. So x minus 3 quantity squared. X plus half of k quantity squared every time. You don't have to think about it, but this one's pretty easy, right? What two numbers multiply to positive 9 and add to negative 6? Negative 3 and negative 3, right? So here it is. Here's my transformation of 4x squared. And obviously, right, if g of x is 4x squared, obviously I've moved this graph where?
3 to the right and 3 to the bottom.
Exactly. So f of x is g of x minus 3 all minus 3, right? So you see I've just replaced the whole mother function with my transformation of it. I would probably like you to say that the vertex is positive 3, negative 3.
And the 4, what role does it play in the graph?
It's a stretcher, so it's going to take so where I would have x squared, right? So there's y equals x squared, and then here's g of x. 1, 2, 3, 4. It stretches out that box, right? So there's y equals 4x squared. And then I'm going to take that new box now and shift it 3 to the right, 1, 2, 3, and 3 down, 1, 2, 3. And now there all of a sudden is my new curve. There's my f of x equals 4 times x minus 3, quantity squared minus 3.
So it's landed to 3 and negative 3?
Yeah, the vertex is 3, negative
Vertex,
3.
okay.
Exactly.
Okay.
Yep.
Okay.
And the stretch is the 4, right? The stretch is the 4. When I'm multiplying on the outside, I'm stretching. Well, I mean, if I'm multiplying by something bigger than 1, I'm stretching. Between 0 and 1, I'm compressing. But it's just a scale factor. And so, Sean, your second question is I mean, I'm not going to do it with the quadratic. I'm going to do it with a I'm going to do a question just like this with a you know, a polynomial, which a quadratic is, but it's too simple, right? So f of x is what? A times x minus z1 times x minus z2. And so the graph that you've given me, oh, it's, yeah, this is tough. Or ax squared plus bx plus c, right? So one of those two, but guess what? It's the second one because they gave me 3 points. So they gave me negative 1, 8, 0, negative 1, and 3, 8. So I got to use the standard form. If they give me zeros, I use the factored form. If they give me points, I use the standard form. If they give me a vertex, I use the vertex form. So I mean, this is a cool problem, but I already know f of 0 is c, so c must be negative 1. Right? We already knew that c was the y-intercept. Right? So f of x is now ax squared plus bx minus 1. So now I'm going to plug in my other 2 points. Right? I'm going to plug in these 2 points and I'll get a system of equations. So when I plug in negative 1, I get a times negative 1 squared plus b times negative 1 minus 1. And that should equal 8. So I get a minus b minus 1 equals 8. There's my first equation in my system. And when I plug in 3, I get a times 3 squared plus b times 3 minus 1, and that should be equal to 8 as well. That's nice. So 9a plus 3b minus 1 equals 8. So there's the second part of my system. So now we're back in.
Sorry, Professor.
Yes.
Could you explain why they're both equal to 8?
That's what was given to me. So they gave me a graph with a quadratic, and they gave me 0.
Got it. Right.
Yeah. So they gave me a bunch of points: negative 1, 8, and 3, 8. So now I just have to solve the system. A minus b minus 1 equals 8, and 9a plus 3b minus 1 equals 8. I'm going to multiply the first one by 3, right? So I get 3a minus 3b minus 3 equals 24, and 9a plus 3b minus 1 equals 8. And I add them, I get 12a equals 12a minus 4 equals 32, or 12a equals 36, so a is 3. And now once I have a, I go back and find b.
Quick question.
Yeah.
Why can't you just subtract both equations from each other?
Before I multiply by 3?
Yeah.
Yeah, nothing would eliminate. So I'm doing something called the elimination method, where if I have opposite coefficients, I can add them together. If I have the same coefficients, I can subtract them.
Sorry, could you repeat that last part?
Yes, if I have opposite coefficients and I don't, right? If I have so a and b are my variables. So if I had opposite coefficients, I could just add them. That's why I multiplied by 3. So my
Okay.
my negative 3b and my positive 3b would cancel.
Okay. Got it.
So on that one's kind of tricky, but on that one I would have gone to the show me an example, and you would have seen them plug in points, right?
Is this going to be on the test?
You could have something like this with a polynomial. Yeah, you should be able to do a problem like this.
And what was the question asking?
Find the quadratic. Find the values of a, b, and c.
Oh, okay.
So they gave me a function. They gave me a graph and 3 points, right? And I know it's got to be I got to use either my zero version, my factored version, or my standard version, or my vertex version. My complete the square version. One of those three. All right, next problem. Okay, on how nice. So this is, it looks like 4-6 again. So this is more of the speed that I'm going to put on your test. I've got r of x is x cubed minus 27 over x squared minus x minus 6. And they're asking for what here on how? I can't see the question.
They're asking for. Sorry, I'm opening up the question on MathXL.
Yeah.
Okay. So they're asking to find the vertical, horizontal, and oblique asymptotes.
Okay, so I do want to factor the numerator, definitely. And remember, first thing I'm doing is graphing. Second thing I'm doing, factoring. Okay, so I want to factor the numerator. I can definitely tell there's a 3 that goes into x cubed minus 27 because 3 cubed is 27. So 27 minus 27 is 0, right? If I didn't recognize that, I would just graph that, and I would see the 3 on the x-axis, right? Downstairs is an easy factor. What is that? That's x minus 3, x plus 2. And you can see why I want to factor, because those two pieces are going to cancel, right? In order for me to get this missing factor here in blue, I'll do synthetic division. So I'm going to try 3 into 1x cubed, 0x squared, 0x minus 27. Everybody with me?
Yeah, so far so good.
Nice. Bring down the first leading coefficient, multiply, add, multiply, add, multiply, add. Good, I got my 0. And now I can tell what goes in here is x squared plus 3x plus 9. How is everybody doing?
You multiplied by 3 because of x minus 3, right? Or...
Yes, because I'm checking to see if 3 is a 0. Right?
Okay.
Yep. Because what makes this 0 is 3, so I'm checking to see if 3 is a 0, and it is.
Quick
Yep.
question. Could
Yep.
you also see if oh wait, no. Could you use -2 here, or would that be an error?
You could have tried, but you would have seen if we did -2. And I like what your thought is, because I got the factors of positive. I got zeros downstairs of 3 and -2, so one of them might cancel, right? So, but if I check the -2, right, I get -35, not a 0.
Okay, why is that?
I mean, it's like why are some people left-handed? It's just
Okay.
Yeah, probably because their parents beat them or something. I don't know. No, they're more creative, right? The left-handers are more creative. I don't know. Okay, so anyway, I have my now factored version of this polynomial, right? And a domain of what? X does not equal -2, x does not equal 3. That's my domain, right? I got to be careful because remember, I'm finding the asymptotes here. So when do I get a vertical asymptote? When the downstairs is 0 and the numerator is not 0, right? So my factored version, my simplified version is just simply x squared plus 3x plus 9 all over x plus 2, but with the same domain. The domain for R of x is all reals minus -2 and 3. I can't put those two in. I gotta, even though I canceled those two pieces that were trouble, I've got to make sure my domain stays the same. So now, vertical asymptotes are only when x equals -2. There is no horizontal asymptote. Does not exist. But there's an oblique, right? And what about, let's find the oblique, right? So I can use my original function to get the oblique, or I can use my simplified version. I'm going to use my simplified version. I'm going to do it with synthetic. In fact, I already did it. No, I didn't. Okay.
Quick question, Professor.
Yes.
So, there's no asymptote at 3.
Correct. There's a hole at 3.
There's a hole. Okay. Is that because they both cancel?
Exactly. And in
top and bottom?
exactly. We call that in calculus a removable discontinuity. There's a hole there, and we can find it and put the manhole cover on it. We can patch it.
Okay.
Mm-hmm.
Okay.
So my oblique is going to come from dividing, or synthetic dividing, -2 into 1, 3, and 9. And I get -2, I get 1, I get -2, I get 7. I get an x plus 1. So y equals x plus 1 is the oblique. So the only thing left to kind of find out about is what happens at x equals 3, right? So we already know there's a hole. Hole at x equals 3. And what I do is I plug in that 3 into my simplified version, 3 squared plus 3 times 3 plus 9 all over 3 plus 2, into my factored version, into my reduced. So I get 27 over 5. So there's a hole at 3 comma 27 fifths. And that's called a removable discontinuity. We know...
So,
go ahead, Joe.
So just for practical purposes, after you find the hole, it doesn't exist.
Yes, but so one of the things we're going to be doing, so I'll pretend it's a roller coaster. If I know where the missing piece is in the roller coaster, I can go fix it. So
okay.
it's all
that
about,
makes more sense.
it's all about finding where that hole is and going to fix it.
Gotcha.
Yeah, because in calculus, if we have continuous functions, we can do a lot more with it. If we have discontinuous functions, we can't do anything with it. And sometimes some of these functions with little holes in them are valuable to us. So we just learn how to patch. We learn how to fix things so that they become useful in a calculus sense. And you know, it's hard to really grasp that, but that's what's going to happen next semester.
Good question.
Yes.
How did you know there was no horizontal asymptote right away?
Because if I look at the long run behavior of this, the mother upstairs is x cubed, the mother downstairs is x squared, and that behaves like x. And look at that thing go. Where does x go? As x goes to infinity, goes forever, up. So remember, I'm looking at the long run of the mother and of the numerator and the denominator, and then I know.
Right. Okay.
Yeah. When that power upstairs is higher, no horizontal asymptote. When the power downstairs is higher, it's a horizontal asymptote of 0. When the powers are the same, then I get a horizontal asymptote of the leading coefficients, the ratio of the leading coefficients.
Okay. Thank you.
Yeah. And in the case...
Professor, could you please repeat that?
Yes. When the numerator, so R of x is n over d, right? If the numerator power is greater than the denominator, the horizontal asymptote does not exist. There may be an oblique, which is a slant asymptote, or a quadratic asymptote, or etc., right? So we're going to stick to obliques, just linear asymptotes. If the numerator is less than the denominator, the horizontal asymptote is y equals 0, right? Because like 1 over x, it'll look like 1 over x or 1 over x squared. And if the numerator power is equal to the denominator, we get a horizontal asymptote of, the leading coefficients. The leading coefficient of the numerator over the leading coefficient of the denominator. And we did one like this already. We did a bunch like that already. All right, good. Thank you for sending me questions. I think that's the best use of time. If you send me the questions, right, send me the questions, and then I can do that. You can get your questions answered quickly. Let's do that again Wednesday, right? Let's move on here. Let's start chapter 5. Yes. So chapter 5, we have to start talking about more kinds of functions, and this is what we're doing for our Calc for Prep 1. We're trying to talk about every possible type of function that I'm going to see in calculus, and that is linear, quadratic, continuing the trend, polynomial, rational, we talked about. I don't know why we don't talk about radicals more, but we did some with the difference quotient. And now we're moving into composition of functions, inverse functions, exponential functions, and logarithmic functions. So that's chapter 5. So chapter 5 in short is composition of functions, inverse functions, exponential functions, and logarithmic functions. And then we're almost done. All we have to do after that are our trigs, right? After we do these, then all that's left is trig. 3 chapters of trig. How is your trig class going? Any comments on your trig class? You're all taking that 1 credit trig class? Easy?
I already took that class.
Nice.
I have not taken that class.
So you're taking it the second half of the semester?
No.
Or you just don't need it? You just don't need it?
Don't need it.
Yep. Because you tested out of it. That's good. Angel, I don't know either. If you want to talk to me right at the end of class. If you were able to register for 165 without registering for 098, I would assume you don't need it. And if you pass 165, it doesn't matter what you get in 098. By the way, if you pass 165 and fail 098, they'll let you move on. Don't do that, though. But, sorry, Alejandra, I missed you there. that it asks you if a point goes through. Oh, well, so once I have an oblique, Alejandro had asked if how can I tell if a point is on the oblique? Once I have the oblique, right? Where's my oblique? I can just plug the XY in and see if it's true, right? Does that make sense?
Wait, I thought a point can't be on an oblique asymptote.
In the short run, it could. In the long run, no.
Okay.
But I think Alejandro was asking me in the chat. It asked me if a point goes through the oblique. I would assume you mean that it is on the oblique, and so you would just check the point, plug in the XY of the point, and see if it's true. If it's true, it's on the oblique. If it's not, it's not on. If it's false, it's not on the oblique. So vertical asymptotes will never touch the graph. Horizontals, obliques, etc. could touch the graph in the short run, but not in the long run. Okay, here we go. So chapter 5, composition of functions, inverse functions, exponential functions, logarithmic functions. So I'm hoping, I don't think this material should confuse you for this test coming up. I'm hoping to at least do 5.1 and start 5.2 before Friday. I might even finish 5.2. And I don't think it will screw you up. And I would say to you, you study for the test, right? You take the test Friday, take a Saturday off, start working on chapter 5 on Sunday, right? Kind of thing, right? I think we're not going to reward ourselves with a whole weekend off until we've got some better grades coming, right? So not feeling like there's enough work being done. Any comment on that?
I can't disagree. I know I've kind of been slacking a bit.
Yeah,
I agree with that.
Yeah, this is why I wear shorts. I hate wearing slacks. All right, here we go. Composition of functions. This is 5.1. Composition of functions. So, I don't know if you heard the news this morning, but they had discovered that Beethoven was buried along with all these pieces of music that no one had ever heard before, so they dug him up. Did you hear this? I just CBS. I don't know if you watched it.
Really?
Yeah. And so they dug him up.
I swear to God, this is a bit.
They dug him up, and he's sitting there erasing, and they asked him, Beethoven, what are you doing? He says, I'm decomposing.
That's a real knee slapper right there.
You started talking about Beethoven. I immediately knew it was a bit.
I mean, I was like, I definitely did not hear this, but I was also thinking that the paper probably would have decomposed by now.
Yeah, no, the paper was, yeah, probably the edges. There was bones and paper in there, that's it. Okay, so what we're talking about of composition of functions, f composed of g of x is a composition of functions. And this is the notation that the book uses, that MathXL uses. I don't like it. Okay, so f composed of g, that little composed symbol, it's like a hollow circle, right? It can be written as this, and this is the one that makes a lot more sense to me. This is the same thing, okay? And you can clearly see that the input of function f is the function g. So when I'm saying composition of functions, I'm saying put an entire function inside of another function. And we've done this already this semester. Where have we done that? Where have we done a composition of functions already?
Difference quotient?
Exactly. When I plugged in x plus h into my function, that's another function, right? So whenever I plug in a more complicated function than x, I'm thinking of a composition of functions. And it's really important in Calc 1 that I can see the inside, right, and the outside function. Right? So our inside used to just be input. Well, now it's the output of a function that we put inside, right? So it's when you do something called the chain rule in Calc 1, it's going to be important for you to be able to see the inside and the outside of the function. And the chain rule in Calc 1 is probably the first part of Calc 1 that's very difficult. And then if you don't get it, you never pass. You never pass Calc 1. So, you know, just find that one YouTube person that really gets you to understand things. Some students like ChemTutor, or I think it's ChemTutor. Some students, I mean, I like Khan Academy, but he's boring as all. You know, there's lots of good people to help you when you get to chain rule. Chain rule is pretty tough. So the first thing we have to be able to do is create a composition of functions, and then of course we have to talk about the domain of composition of functions. Okay, so that's really kind of our two main things. The book also talks about this inside-outside piece. Maybe we'll look at that, but there's none of them in the homework. Okay, so let's do three things with this today. Let's do some compositions via table and actual functions. Let's look at the domain and talk about the theory behind the domain, what has to happen with the domain, and then maybe this inside-outside piece. So let's start with just plain old composition of functions, because that's the main thing I need you to be able to do, right? So composition examples. So let's say f of x is x squared, g of x is x minus 3. Right? So I can see the two functions, and we're going to find the composition h of x, which is f composed of g of x. And remember, whenever you see that f composed of g, I'm writing it this way. I think it's a lot easier to understand. What I like to do is I like to write my outside function first. What is my outside function?
F.
Yes, good. So x squared with empty parens. And then what am I putting in, right? So you can see my outside function, and what am I putting into that? My inside function, x minus 3. So I'm taking my time like that, rewriting the outside function with empty paren, plugging in with the inside function, right? And so here's my function h of x now, x minus 3 quantity squared, or what? X squared minus 6x plus 9, right? There's h of x. What's the domain of f here? Is anything, right? What's the domain of g here? Is anything, right? So in this case, I might be safe, but if I now go look at h and I ask what's that domain, obviously anything goes there, right? So when I have these really functions that are open to any input, they should be pretty safe in my composition of functions. And the real special piece here is that those particular functions that I'm composing are continuous. There's no holes in the roller coaster, right, in the track. So I want to take a look at something. I want to take a look at, let's say, g of 2. What is g of 2?
minus 1.
Yes, so that's 2 minus 3, that's a negative 1, right? And I want to take, because look at what's happening inside of the function f, is I'm working on g, and g is generating, right? So look at f of g of 2 is now f of minus 1. So now I want to find f of minus 1, right? The output of g is going to become domain of f, right? And this is an important thought for me. I want to be thinking, I got to be careful with the outputs of g that don't work with f. Now, since they're both continuous everywhere, it doesn't matter, right? So, but what is f of negative 1? That's negative 1 squared. That's positive 1, right? Everybody with me?
Yes.
Good. So
Yeah, that makes sense.
yeah, so my original input is 2, and then g generates an output, which becomes the input of the outside function, and then I generate what comes from that. So I want to look at h of 2 now, right? And what am I going to put in h? I'm going to put in the original domain that I talked about. So I have 2 squared minus 6 times 2 plus 9. And I got 4 minus 12 plus 9. So 13 minus 12. And you see it gives me the same output of my, right, this new function that I've generated gives me the same output as my composition of functions, because it is my composition of functions, right? All right, let's take a look at another one. So let's take f of x is x minus 1 over x, and let's take g of x to be 1 over x. And let's talk about the domain of these guys first. This is the domain of g.
X can equal 0.
Nice. What is the domain of f?
X can equal 0.
Nice. So that means I have to make sure g of x does not equal 0. And of course, g of x can never equal 0. Right? So I can already tell what my domain is of my new function, of my composition of functions. It's going to be x not equal to 0. I have to make sure I keep the domain of g, and I check the domain of f with the output of g, because remember, g is generating the inputs of f. Everyone okay there? So let's find h of x, which is f composed of g. And that notation sucks, so I like to use this one, because I can clearly see I'm putting g of x inside. And so what am I going to do here? Empty parens for x in the outside function. And in there, I'm putting in my 1 over x. Everybody okay here?
Yeah.
So I want to kind of simplify this thing a little bit. And the way I do this is called a complex fraction, is I take my LCD and multiply numerator and denominator by the LCD, right? So I take x over x and multiply. And what do I get here? I get 1 minus x over 1. Now, a little bit strange in looking at this, because this is just 1 minus x, right? My composition is 1 minus x, but I have to remember I cannot use 0 here. I cannot use 0 here, right? Because it's not in my original function. So in this composition of functions, I have to adopt that domain. I have to adopt the domain from the original functions. And you'll see why in a second. Let's pick x is 2. That's not a problem, right? So let's find h of 2. I'm just using 2 again. That's lucky guess. So what do I get? I get 1 minus 2 is negative 1. So when I do the compositions with 2, I get a result of negative 1. But let's find g of 2. What's g of 2? 1/2, right? Let's find f of g of 2, which is f of 1/2, which is 1/2 minus 1 over 1/2. So that's minus 1/2 over 1/2, which is minus 1. And we get the same result. In a computer science aspect of what's happening here, I'm generating this new function that's a lot faster than using the 2 original functions, right? And it's all about that kind of speed, right? Can I, if I have these 2 machines working together, can I just create a single machine, right? Imagine I have a machine inside that's digging the dirt and filtering out the gold, and the second machine it's taking the gold and melting it down. And now I have just one machine that's digging the dirt and melting the gold down, right? So thinking about that inside piece and the outside piece. What am I starting with? The dirt. What am I ending with? The molten gold kind of thing.
Professor?
Yes.
Could you explain why you multiplied h of x by x over x?
Yes, whenever I have something called a complex fraction, fractions within fractions, I always want to do this little LCD thing. And we did that with our difference quotient. Remember that? So I want to,
right.
It's called clearing fractions. So you're trying to always get a single numerator factored and a single denominator factored, instead of having multiple numerators and denominators inside of one.
Okay, but you're not altering the function in
Correct. I must adopt the domain of the originals.
Okay.
So h of x, right? H of x, what I got is h of x only equals my composition if I keep the same domain.
Right.
If I change the domain, like if I look at just this new h of x and just get the domain of that, which is everything, it's not the same function anymore.
Okay. Okay, got it.
Like on this one, I can plug in 0, right? H of 0 exists, right? H of 0 is 1 minus 0, it's 1. But when I go to g and plug in 0, I get 1 over 0, and I'm in trouble, right?
Okay, so when you graph h of x, there would be
yes, there
a discontinuity.
Exactly.
At 0. Okay.
Exactly.
Okay. Got it.
Yep. Nice. Let's look at one with the table. The tables are a little bit tougher. Only because I think we tend to be impatient, us humans. So this is from the textbook. We could look at number 9. 9a, f composed of g of 1. Right? F composed of g of 1. Let me see if I can get a decent... Sorry, trying. There we go. F composed of g of 1. I'm going to try and do this without... 9a, f composed of g of 1. What's my original input? Part A, f composed of g of 1, right?
G is the input?
1 is the input, right? And what function am I putting it into?
On G.
On G. So G of 1, you can see where my X is. Can you see my mouse moving on X?
Yeah.
Yes. So I want G of 1. So I'm putting in 1, and here is G of 1. That's 0. And so now what am I putting into F? I'm putting 0, and what do I get out of F? I get a -1. Yeah.
That's way more easier.
Okay. Some students don't like it at all, but I never test on the table. But there's a couple of tables on the in the homework, so just make sure you do those because it will help you understand it. Go ahead, Angel.
Yeah, what would part E
Sure.
be?
So G composed of itself of -2. So put in -2 to G. I put in -2 to G. I get a 3 out. And now put that result back into G. So what do I put into G? I put in a 3, and what do I get out? An 8.
Okay, that's a bit strange. But
Yeah, and there's some beautiful, beautiful functions when you, it's called iteration, when you use the function and compose it with itself, some really fantastic things happen in nature. And for me, it's growth. It's how humans grow, that type of thing.
Isn't that how fractals happen?
Exactly, that's a fractal. Self-similarity, self-iteration. So if you took a big piece of broccoli and broke off one stem and looked at that, it looks just like a big piece of broccoli, et cetera, et cetera. So when things grow, they self-generate. So it's related to composition of functions among themselves. It's quite a beautiful thing. Let's take a look at another one here, where I'm going to give you, so here's a bunch in the book where they ask you to do compositions, right? We just did a couple of them. And then I wanted to look at this inside-outside piece. So here again, find all these compositions, F composed of G, G composed of F, F composed of F, G composed of G, all done the same way I did them. And here it is. Here's number 47 to 52 is, can you find the outside function and the inside function? So let's take H, right? H is square root of x squared plus 1. There's no homework like this, and I won't ask you this, but you'll do it in Calc 2, as Calc 1. So if h of x is the square root of x squared plus 1, tell me the outside function.
Root x.
Nice. And the inside function?
X squared plus 1.
Nice. Someone else give me something different. I'll say the outside function is root x again. Oh no, I won't say the outside function is root x. Someone give me something different. Other than Joe, someone else.
Root x squared? Or, wait, no, that doesn't make sense.
Yeah, almost. Yep, almost.
I'm not sure.
It's not easy to do this right away. It takes a little bit of practice. But if you can imagine I'm plugging in x squared, right? What would I have to plug in x squared to get x squared plus 1?
Could it just be 1?
Almost.
1?
I have to plug it in somewhere, right?
Plus 1?
X plus 1, yeah. I always have to plug into empty parens, right?
Okay.
Yeah. So those are weird, but those are fun to do, and you'll do them in Calc 1 quite a bit. Especially if you take if you take Calc 1 with me, I talk about that. When I do chain rule, I talk about the inside-outside all the time because it's a lot easier than talking about it the way the super nerds talk about it. Let me do 2 more compositions today, and then we'll see if we can move on to 5.2 a little bit. How are we feeling about this? Pretty easy?
Okay, so far.
Good, let's do this composition. Let's do H composed of G. Sorry, F composed of G. So what's my outside function is 1 over x, and I'm putting in empty parens. 1 over empty parens, right? And then what am I putting in there? The inside function g of x, I'm putting in 1 over x. And this is just my keep change flip, right? And so what do I get here? I get 1 times x over 1, which is just x. There's something special about a composition of functions that has a result of x. Okay? There's something special about a composition of functions that has the result of x. But I have to make sure for this thing that's special, it has to make sure I work it both ways. I have to do f composed of g and g composed of f. Obviously, since they're the same, I'm going to get the same result here, right? So if j of x is g composed of f, I get the same result, right? That's also x. So when I do these, check these 2 compositions and I get the result of x, these functions are called inverse of each other. They undo each other. Okay, let's look at another one. Now you could have functions that if you do f composed of g, you get x, but g composed of f, you don't. Okay, so this is why you always have to check both, right? But right now the book will be prompting you. Let's look at another one here. Let's see, f of x is 2x plus 1, and g of x is x minus 1 all over 2. These are also undo each other, and we can look at that first. Let's put a 3 into f. Right? Let's put a 3 into f. What do I get?
7.
Yes. 2 times 3 plus 1 is 7. So let's put a 7 into g. And I get 7 minus 1 over 2. That's 6 over 2. That's 3. So you see, I started with a 3, went to a 7, then I went into my inverse machine, put in the 7, got back to 3, right? So let's do the composition now. So you're going along with me. Let's do h of x is f composed of g. So my outside function is 2x plus 1. Notice I put in empty parens. Let me take attendance real quick. We're down to, what are we down to, 23 students? My other class is down to 21. Four, 8, 12, 16, 20, 21. I'm missing 2 students. Max is not here. Oh, Max is here. Max is here. I see you. All right, so inside of this, I'm putting my x minus 1 over 2. The 2's will cancel. We get x minus 1 plus 1. We get x. Huh. What do you know? If I do g composed of f, I get parenthesis minus 1 all over 2, and I'm putting into that 2x plus 1. So I get 2x plus 1 minus 1 all over 2, which is 2x over 2, which is x. Hey, that's it. So this is going to be a nice way for us to check if we have inverse functions. If we have functions that will undo each other, right? If we have functions that will undo each other, I mean, you don't want to just learn to drive forward, right? You also want to, you have to be able to go in reverse, right? Unless you, just park against some building and leave it there for the rest of your life, right? So
Yeah, just get in a car facing the other direction.
there you go. So I think we're ready to move on. You got to practice this composition of functions. It takes quite a bit of practice. Okay, so you just have to do a bunch of problems. Don't do only the MathXL, please. Do the problems in the book. And what problems do I like in the book? I like for the compositions, I like 23 to 37. And the ones I really like are the fractions. Right? All of the ones with the fractions, that's the one I'm going to put on your test. Here's some nice practice, 39 to 46, the inverse ones, right? And you can see 46 is the one I did already, 1 over x and 1 over x. It's pretty rare that you can have a function be an inverse to itself, but there are a few, and they're special, for sure. Nice. Let's look at 5.2. Are we okay here?
Yeah.
Yes.
Nice. I'm assuming that you're going to bombard me Wednesday with questions. So I'm assuming I'm not going to be able to do much new material. I'm hoping you do. Oh my God, please. If your average is under 60, what was your average last time? 60? 59? I'll probably just give up. I'll quit teaching and just go do something else.
No, don't quit teaching.
I don't know when.
You said you would go make pizza.
Oh yeah, pizza. The pizza will never die. People will eat pizza for forever. All right, inverse functions. So let's look at some notation, right, first. F of x, let's do the one we just had, 2x plus 1, and g of x equal x minus 1 over 2 are inverse functions. If and only if f composed of g equals g composed of f equals x. And typically, g of x is called f inverse of x. Right? Red is red f inverse of x. So it looks like f to the minus 1 power, but it's not. Okay? It's not f to the minus 1 power. It is the inverse function, right? So I typically like to just use the letter. If they give me an inverse, I'll change it. If they give me f inverse notation, I'll change it to g usually, and just keep in mind that I know that they're inverse functions of each other. So just be careful about thinking of that as being reciprocal. It's not, right? It's not a reciprocal. You know, and I'm trying to write as little as possible, so I don't like to write all of this. I'd rather write G. It's just a lot, you know, a lot more basic. So the question really is when does a function have an inverse? Do all functions have inverses? No. So when does a function have an inverse? Well, if you think about it, if you think about what's happening, what happens to my x's when I right? You remember what I had before, right? What did I have before? Let me go back to that. Well, I can do it here. I had f of x is 2x plus 1, and I plugged in a 3, right? And I got out a 7. And then I had g of x is x minus 1 all over 2, and I plugged in a 7, and I got out a 3. So what happens to my domain and range? What's happening to my domain and range when I'm looking at inverse functions?
Are they also inverted? Or
yes, exactly.
they
switch. They switch. That's it. Right. Exactly it. So, I'm, my x values become y values and vice versa. So now if I think about this guy having to be a function, for every unique input, there's one and only one output. Now that also has to be true about g. G must also be a function. So for every unique input, there's one and only one output. But guess what? G's inputs are the outputs of my original. Okay? So it turns out that we say f has an inverse if it's 1 to 1. F has an inverse f to the minus 1 of x, which I'll call g, right? If f is 1 to 1. So it's a function to begin with, and then for every unique y, there's only one x. F is a function, and for every y, there is only one, and there's one and only one x. That exclamation point means unique. For every unique y. But it's pretty easy. It must pass the horizontal line test to be a function. HLT. It must pass the vertical line test. Sorry, it must pass the vertical line test to be a function. Vertical line test to be a function, and it must pass the horizontal line test to be 1 to 1. So if I pick one y value, right, there should only be one x for it. If I pick any unique y value, there should only be one x. Another way to say it, if f of a equals f of b, so notice there I have two y values or two x values. Do I have equal y values or equal x values there?
Equal what?
Two equal y values. So I have the same height, then a must be equal to b. I must have the same x's. If I have the same height, I must have the same x's. If I have different x's, then what must be true about the y's? If I pick two different x's on they must be different. Yes, then f of a cannot equal f of b. And this is my 1-to-1 function definition. Same y's must be same x's. Different x's must be same y's. I can have no repeated heights. That's another way of saying it. I like that one the most. I can have no repeated heights. If I have any repeated heights, right, I've got a repeated height. I will have different x values there. I need to, for every unique height, for every repeated height, only one x value. Just like for every unique x value, there's only one y value. I need the function and its inverse to be a function in order for the inverse to exist. And that's easier said as saying the function must be 1-to-1. Show the following function is 1-to-1. Let's see, f of x is 2x plus 1. We already did this, right? This one's obvious. We already know the inverse, right? So we're going to let f of a equal f of b and show a equals b. Ready? So let f of a equal 2a plus 1 and f of b equal 2b plus 1. Knowing 2a plus 1 equals 2b plus 1, show a equals b. Easy, right? What are we going to do? Subtract 1 from both sides. So 2a equals 2b. Divide both by 2. So a equals b. QED. The book won't ask you to do this. I would like you to. If I ask you to show that a function is 1-to-1, or if I say that the function is 1-to-1, it'd be nice if you verify it for me. I'm trying to get MathXL to give you all the same question. I can't do it. I don't know what to do. I got 2 days to figure it out. Let's do another one. Show the following function is 1-to-1. So what does it mean when it's 1-to-1? It means I can find the inverse. How do we find the inverse? Takes a little bit of work. Okay. But if you think about, this is important. If my domain and range switch, if my x's and y's switch, I know how to find the domain of a function. How will I now be able to find the range of a function? I'm going to create the inverse and find its domain, and that will give me the range of the original function. Since the x's and y's switch, and it's easy to find domain, if my function is 1-to-1, I can easily find the range of the function by finding the domain of the inverse. I'll write all that down a little bit. I'm not going to get all this done in 3 minutes, but that's okay. Let's just do one more. F of x equals x over x minus 3. Let's show it's 1-to-1. So what do I want? I want a over a minus 3 to be equal to b over b minus 3. And I want to show that these two pieces are, a and b are equal, right? So any idea what to do here?
Do you have to make the denominators the same?
You could. It's easier than that. Get rid of the denominators.
Get rid of.
Yep.
Yeah.
Yeah. Cross multiply. So I get AB minus 3A equals AB minus 3B. And obviously the AB's go away. And I divide by -3, I get A equals B. Done. All right, you're not ready to start 5.2, but you can certainly start 5.1. I'm expecting questions from you Wednesday. You have lots of work to do. Please, please get some work done. I'll see you Wednesday.
Have a good one, Professor.
Bye,
Thank you,
Professor.
Professor. You have a great day.
Thank you.
Professor.
Thank you, Professor.